Imagine a place where time loses its value. A space beyond the reach of light, where the cosmic cold freezes all movement, where the temperature approaches absolute zero, profoundly lonely. In that chillingly silent eternal void, there is a silent traveler, drifting aimlessly. It does not have the sleek shape of a sci-fi spaceship, no elite crew, no red-hot jet engines. It just keeps going into the dark night, for a single reason. It was launched by humanity in the fall of 1977. While we are peacefully breathing, tens of billions of kilometers away, that piece of metal stubbornly presses on. The engineers who once touched its aluminum shell now lie deep beneath the cold earth. Yet, their creation is carrying out a mission 1,000,000 times greater. Exploring the universe. To understand why a rudimentary mechanical structure can challenge time, we must return to the summer of 1977, the peak of the Cold War. The space race between the US and the Soviet Union was an arena to assert national power, where every scientific achievement was tied to national pride. Regarding technology, personal computers were still very rare. The internet did not exist, and smartphones were beyond imagination. Voyager 1's memory was only about 69 kilobytes, tens of thousands of times smaller than a modern selfie. Data was stored on digital magnetic tape, and engineers had to program in assembly, optimizing every bit of data and checking algorithms by hand. The onboard computer system was so weak that it relied almost entirely on commands transmitted from Earth. However, scientists still pursued a bold vision. Initially, the project was named Grand Tour, with the ambition of sending a spacecraft to visit all the outer planets. When the budget was cut due to the oil crisis, NASA was forced to scale back the plan and rename it Voyager. But at JPL, scientists took advantage of a rare astronomical opportunity that occurs only once every 175 years. The person who discovered this opportunity was Gary Flandreau. In 1965, he realized that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would align in a special orbital arc. Thanks to this, a spacecraft could visit all 4 planets in a single journey, shortening the flight time from about 30 years to 12 years. The key to the plan was the gravity assist technique. Instead of relying entirely on chemical fuel, Voyager would use the gravity of planets like natural slingshots. When passing a planet, the spacecraft gains velocity by borrowing a tiny portion of kinetic energy from its orbit. For the planets, this loss is nearly negligible. But for Voyager, it was a massive boost that saved tons of fuel and years of travel. If they missed the summer of 1977, humanity would have to wait until the 22nd century for a similar opportunity. Therefore, on September 5th, 1977, Voyager 1 was launched from Cape Canaveral on a Titan IIIe Centaur rocket, carrying the exploratory aspirations of all humanity. Although Voyager 2 was launched 2 weeks earlier, Voyager 1 was chosen for a shorter trajectory and quickly took the lead. Scientists understood that this was a one-way trip. Therefore, they placed a special treasure on board, the Golden Record. Under the guidance of Carl Sagan, it was created as a message sent into the cosmic ocean. The gold-plated copper record was designed to last for billions of years, complete with a needle and instructions for use. On the protective cover, they did not use any human language, but instead engraved mathematical symbols, basic physics, and a diagram determining Earth's position based on 14 pulsars. These cosmic lighthouses have unique signals, allowing any advanced civilization to trace the location of the solar system. Inside the Golden Record is a miniature portrait of Earth. 115 images of DNA, humans, animals, nature, architecture, and life. There are also sounds of ocean waves, thunder, a baby's cry, and greetings in 55 languages. Notably, the record also preserves the heartbeat and brainwaves of Anne Druyan, who later became Carl Sagan's wife, as a message of love sent into space. Along with that are musical masterpieces ranging from Bach, Mozart, and Beethoven to Chuck Berry's rock and roll Johnny B. Good, plus many folk melodies from around the world. Before letting Voyager 1 plunge into interstellar space, humanity sent along its most beautiful things: knowledge, art, love, and the story of Earth's existence. In March 1979, after 2 years of crossing the asteroid belt between Mars and Jupiter, Voyager 1 approached its first major target, Jupiter, the lord of the solar system. The vast distance between Jupiter and Earth meant that image signals took tens of minutes to reach JPL. Each photo appeared one slow line of pixels at a time on the screen. Before that, human knowledge of Jupiter was based only on faint observations from telescopes. But as Voyager 1 drew near, it opened up a completely different world, forcing scientists to rewrite much of astronomical knowledge. Jupiter does not have a solid surface like Earth, but is a gas giant, primarily composed of hydrogen and helium. It dominates the solar system in mass and magnetic field. The deeper one goes, the more the atmospheric pressure increases until hydrogen turns into a liquid state, forming a massive conductive hydrogen ocean beneath the cloud layers. Voyager 1's cameras recorded a violent atmosphere with swirling bands of brown and yellow clouds. Wind speeds could reach 1,500 kilometers per hour, enough to destroy any man-made structure. The cloud bands move in opposite directions, creating areas of intense turbulence and cyclones. Most prominent is the Great Red Spot in the southern hemisphere, a massive storm that has existed for over 300 years. At the time Voyager 1 visited, it was more than 16,000 kilometers wide, large enough to contain 2 to 3 Earths. Swirling clouds of frozen ammonia around the storm's center create one of the most majestic atmospheric phenomena in the solar system. If Earth were inside that storm, it would completely disappear under Jupiter's massive and toxic cloud layers. However, Voyager 1's most shocking discovery was not Jupiter itself, but its moons. Previously, astronomers believed these moons were just dead blocks of rock and ice. But when flying past Io, Voyager 1 captured an unprecedented sight: plumes of sulfurous material erupting hundreds of kilometers into space. The first person to recognize this phenomenon was engineer Linda Morabito. She determined it was not an image error, but an active volcano. This was the first time humans observed volcanic activity on a celestial body other than Earth. The cause stems from Jupiter's extremely strong gravity and the orbital resonance between Io, Europa, and Ganymede. This effect constantly distorts Io's internal structure, creating enough friction to melt its interior. As a result, Io became a world of sulfur and boiling lava, as well as the most geologically active celestial body in the solar system. Continuing its journey, Voyager 1 approached Europa. In contrast to Io, Europa is an icy sphere covered in long brown cracks. Its surface is very flat, with few impact craters, indicating that the ice layer is continuously regenerated from material below. These images gave rise to a revolutionary hypothesis. Beneath Europa's tens of kilometers thick ice layer, there may exist a massive liquid water ocean, containing more water than all the oceans on Earth combined. Heat from tidal forces created by Jupiter could keep this ocean from freezing. Consequently, Europa became one of the leading candidates for extraterrestrial life. But to obtain those precious data, Voyager 1 had to face a life-or-death challenge. During the gravity assist maneuver, it was forced to fly through Jupiter's massive magnetosphere, which contains the strongest radiation belts in the solar system. Electrons and protons accelerated to near the speed of light, created radiation levels far exceeding human tolerance. Onboard electronic components were constantly bombarded. The central computer was disrupted, optical sensors were affected, and random data errors appeared in the memory. Due to the extreme distance, engineers on Earth could only watch in anxiety, as radio signals took tens of minutes to transmit. Thanks to its durable design and pre-prepared radiation shielding, Voyager 1 ultimately survived the danger zone. Not only did it overcome the challenge, it also used Jupiter's gravity to accelerate to over 25 kilometers per second, continuing towards Saturn and the next leg of its journey. In November 1980, after more than a year of crossing the space between planets, Voyager 1 approached Saturn, nature's masterpiece with its famous ring system. From Earth, Saturn's rings look like a thin and graceful silk ribbon. But at close range, Voyager 1 discovered it was an extremely complex structure consisting of countless small rings packed together like grooves on a vinyl record. This system spans up to 280,000 kilometers, but its average thickness is only about 10 meters, a staggering paradox. It is made up of billions of pieces of water ice and rock dust, ranging in size from grains of sand to blocks as large as a house. These pieces of material orbit the planet at extremely high speeds and are maintained by the gravity of shepherd moons like Prometheus and Pandora. Voyager 1 also discovered structures resembling bicycle spokes appearing on the rings, which were actually clouds of charged dust lifted by Saturn's magnetic field. However, the mission's most important target was not the rings, but Titan, Saturn's largest and most mysterious moon. Titan is the only moon in the solar system with a dense atmosphere, with a surface pressure about 1.5 times higher than Earth's. Voyager 1's optical cameras could not see through the thick orange cloud layer covering the entire surface. This haze is made of complex organic compounds called tholins, formed when ultraviolet light breaks down methane and nitrogen. Nevertheless, Voyager 1's spectrometers and radio instruments provided a major discovery. At temperatures around -180 degrees Celsius, methane on Titan exists simultaneously in gas, liquid, and solid forms. Titan is seen as a portrait of prebiotic Earth billions of years ago. Here, instead of a water cycle, nature operates with methane and ethane. Methane rain falls to the surface, forming rivers and canyons and flowing into massive hydrocarbon seas like Kraken Mare. This is a natural chemical laboratory where organic compounds are constantly forming and could be the precursor for life in the far future. To study Titan at a distance of only 4,000 kilometers, NASA had to make a decision involving a significant trade-off. They used Titan's gravity to bend Voyager 1's orbit, helping to collect the most valuable atmospheric data. This decision was a scientific success, but also ended the rest of the outer planet exploration journey. Titan's gravity pushed Voyager 1 off the ecliptic plane and hurled it toward the north of the solar system. This meant Voyager 1 gave up the opportunity to visit Uranus and Neptune like Voyager 2. Since the fateful encounter with Titan, the spacecraft has embarked on a one-way journey, leaving the solar system forever, heading straight into interstellar space and the vast void of the Milky Way. Ten years after the historic turn at Titan, in 1990, Voyager 1 was nearly 6 billion kilometers from Earth, far beyond the orbit of Pluto and entering the cold outer reaches of the solar system. Power was slowly declining, forcing scientists to prepare to permanently shut down the camera system to save energy for the remaining scientific instruments. At that moment, astronomer Carl Sagan made a bold proposal: turn Voyager 1's camera around to take a final photo of Earth before the system stopped working. Many NASA engineers fiercely objected. They feared that pointing the camera toward the sun could damage the sensors, consume precious hydrazine fuel, and yield no significant scientific value. At a distance of 6 billion kilometers, Earth only appeared as a tiny, almost meaningless point of light in the photo. But Carl Sagan saw the issue from a philosophical rather than a technical perspective. He argued that humanity needed a symbol to clearly realize its place in the universe. Using his influence and persuasive skills, he convinced NASA leadership to approve the plan. After much debate, the command was sent. Voyager 1 slowly turned, pointing its camera toward its distant home and taking the historic photo titled "Pale Blue Dot." When the photo was processed, it showed a dark scene of deep space, intersected by light streaks caused by sunlight reflecting in the lens. Nestled in one of those light rays was a blue dot, so small it was less than a single pixel. Earth. Looking at the photo, Carl Sagan wrote his famous lines. "That is where every human who ever lived resided, every joy and pain, every king, peasant, inventor, lover, saint and sinner in history. All existed on a tiny mote of dust suspended in a sunbeam of the universe." The photo serves as a reminder that human pride and sense of self-importance become meaningless before the vast scale of the universe. Pale blue dot later became a cultural and philosophical icon, helping to shape global awareness about environmental protection. It reminds us that Earth is the only home for life known to humanity, and there is nowhere else to replace it if we destroy it ourselves. After completing that final mission, Voyager 1's camera system was turned off permanently to save energy. The associated memory was freed up for other critical functions. From that moment, the spacecraft continued to plunge into the darkness of interstellar space in a deliberate blindness. More accurately, Voyager 1 had completed the seeing part of its mission. It no longer had the capability to observe Earth or the planets. From then on, it only felt the universe through charged particle detectors and magnetic field sensors still functioning on board. Voyager 1's journey continued in silence for the next 2 decades, crossing empty space after empty space in the frontier regions. It passed through the terminal shock in 2004. This is where the solar wind begins to slow down below the speed of sound due to collisions with the interstellar medium. Until August 25, 2012, another great and landmark milestone for human civilization was established by this resilient entity. Voyager 1 officially reached the heliopause. This is the ultimate boundary, the invisible border of the solar system, where the solar wind containing charged particles is extinguished and pushed back entirely by the opposing pressure of the interstellar medium. On that day, the onboard particle detectors recorded a historic fluctuation. The density of low-energy particles originating from inside the heliosphere suddenly dropped sharply to near zero. Conversely, the density of cosmic rays from the deep space of the Milky Way suddenly surged to double. This proved that the Sun's magnetic protective layer no longer enveloped the spacecraft. It had stepped out into the open space of the galaxy. Voyager 1 did something that no man-made object in history had done before. It completely escaped the protective flow of its parent star, taking humanity's first steps into interstellar space. It officially became a free traveler of the Milky Way, no longer bound by the particle thrust from the star that gave birth to it. As of the current time in 2026, the spacecraft is at an unimaginable distance from Earth, far beyond any conventional human thought patterns, over 25.9 billion kilometers. This distance is equivalent to more than 173 astronomical units, AU, meaning 173 times the distance from Earth to the Sun. This distance has reached a milestone that redefines the concept of space. One light day. Imagine the terror of this distance through physical velocity. Light travels at 300,000 kilometers per second, yet it takes a full 24 hours of continuous travel to go from Voyager 1's antenna back to the giant radio telescopes of the Deep Space Network, DSN, located in California, Madrid, and Canberra. A control command encoded and sent by NASA engineers today would not reach the spacecraft until tomorrow, and they would have to wait until the day after tomorrow to receive a confirmation signal back from it. The conversation between humans and their child now requires 48 hours for a single cycle. Every control operation must be pre-programmed and anticipate the future. There is no room for error. One wrong command could cause the spacecraft to turn its antenna away from Earth and lose contact forever. The difficulty is multiplied given that Voyager 1's current journey has become a silent, skillful, and painful survival battle in the heart of the cold universe. The only energy source maintaining life and operations for all onboard systems is the plutonium-238 radioisotope thermoelectric generator, RTG. It works by converting heat generated from the radioactive decay of plutonium into electricity. According to the natural laws of radioactive decay, the half-life of plutonium-238 is 87.7 years, causing the power output of this core to continuously drop by about 4 watts per year irrecoverably. To save every last drop of energy and extend the spacecraft's life, engineers at NASA have been forced to make heart-wrenching decisions over the years. They have had to gradually turn off each precious scientific instrument that once achieved so many glorious feats. They turned off the heating systems for particle detectors, forcing delicate components to operate in the freezing cold of deep space. And then, they had to turn off the heater for the main antenna pointing toward Earth. They turned off the ultraviolet scanner, the infrared spectrometer, and the plasma system. This aging and harshness led to a terrifying incident in early 2024. Voyager 1's central computer system unexpectedly experienced a hardware failure in a memory chip belonging to the Flight Data System, FDS. The FDS is responsible for collecting scientific data and packaging it into code to transmit back to Earth. When this memory chip failed due to the passage of time and radiation, the spacecraft could not compile scientific data. It continuously sent back to Earth meaningless binary code, a repeating sequence of ones and zeros over and over, like a hopeless moan in the cosmic darkness. For months, a group of veteran NASA engineers, people with white hair who had been with the project since the 70s, had to look back at yellowed handwritten manuals from half a century ago. They had to relearn how to think like engineers from the crude mechanical era. They worked racing against time, sending each line of repair commands across a one-light-day distance. They could not replace a broken memory chip from 25 billion kilometers away. The only solution was to break up the FDS command code and scatter it into other healthy memory areas. And once again, through a technological miracle and genius perseverance, they successfully restructured the memory, moving the failed code area to another partition. Rescuing Voyager 1 from the brink of death, they returned it to normal operation in mid-2024. That was one of the greatest technological rescue feats in the history of the aerospace industry. The spacecraft currently still operates in a cold environment near absolute zero. With a total remaining power output of less than 200 watts, that tiny amount of electricity is less than the power of a small hairdryer or a common incandescent light bulb in your house. To keep the spacecraft stable, engineers even had to activate backup thrusters that had not been used for 40 years. And miraculously, these thrusters still worked perfectly when they received the command. Yet, despite the destructive cold of interstellar space, and despite the severe energy shortage threatening every hour, the mechanical heart of the traveler beats resiliently. It accepts blinding and deafening itself, sacrificing peripheral parts to maintain its final breaths, keeping the invisible umbilical cord to its home on Earth from being severed. But every journey has an end. Every source of energy in the universe must follow the laws of physics, including energy from plutonium. According to engineer calculations, by the late 2030s, Voyager 1's electrical power will drop below the minimum level to operate the computer system and the radio transmitter. When that day comes, the final communication link between Voyager 1 and Earth will be cut forever. Interstellar space will become completely silent for the spacecraft. Voyager 1's death will not be dramatic. It will not explode or collide with any celestial body. It will simply stop answering. Radio telescopes on Earth will receive nothing but the background noise of the universe. From then on, Voyager 1 returns to its original nature, a small metal machine, alone in deep space. No one watching, no one knowing its journey, and no possibility of rescue. In about 300 years, the spacecraft will enter the inner edge of the Oort cloud, the massive reservoir of comets surrounding the solar system. It will take about 30,000 years to completely pass through this region. After about 40,000 years, Voyager 1 will pass the star AC plus 79,38888 at a distance of 1.6 light-years and continue to orbit the center of the Milky Way in an orbit lasting about 225 million years per revolution. If we push the timeline forward to 10 trillion years in the future, nearly 1,000 times longer than the current age of the universe will enter its era of decline. Every star like the Sun will have long ago run out of fuel. Even red dwarfs, the longest living stars, will have faded and turned into cold, dark bodies. Galaxies then will be nothing more than massive graveyards containing black holes and dead stellar remnants. The sky will have no light, no nuclear reactions, and no trace of life. The universe will be plunged into darkness and absolute silence. If it does not collide with any celestial body or get swallowed by a black hole, Voyager 1 at that time will be older than any active star. It will become a fossil of the age of light, a witness to the era when the universe was once warm, brilliant, and full of energy. Further into the future, according to some modern physics theories, the proton, the basic component of matter, may begin to decay. When that happens, the steel, aluminum, and even the golden record of Voyager 1 will be unable to maintain their atomic structure. The spacecraft will gradually disintegrate into elementary particles, merging into the infinitely expanding space. It will have no form, no memory, and no identifiable physical trace. The end of Voyager 1 will coincide with the decay of matter itself in the universe. But before that happens, remember what this tiny entity achieved. Voyager 1 has gone further than any living creature, idea, empire, or civilization that ever appeared on Earth. It carries humanity's message across astronomical eras toward the threshold of eternity. And as long as the atoms of the golden record still exist, that message will continue to drift in space. That in the middle of a vast, cold, and nearly empty universe, there once was a blue planet named Earth. There once was a species called humans, creatures who knew how to look up at the starry sky with infinite curiosity and dared to reach out their small hands to touch the infinite. Thank you for accompanying Voyager 1 through the great eras of time and space.